Okay, this is, well, believe it or not, it's lecture 26. And we'll have one more after this. It's the last week of classes, right? How does everyone feel about that? Probably a hectic time of the semester. Okay, we'll continue on multiprocessing. Hopefully you're enjoying it. This is how all processors are designed today, so it's important to know. But a reminder, I'll talk more about this soon. Lab assignment 7 is out. It's about an exciting topic, cache coherence, which we will cover in more detail today. It's due May 4th, but we've decided you can use 2 additional days without any penalty, May 6th. And there are no additional days for any lab after May 6th.
So if you have like 4 late days, you can't use them?
No, you cannot use them for lab 6. Unfortunately, because I don't want you guys spending your time on the exam. Okay, is that reasonable? Is that, does anyone want to use late days?
I have a final on.
Yeah, there's a final on Thursday, so. But we will grade everything fairly, and we will curve the course as we have done so far. So don't worry too much about it. But do it for learning. I would say this is an important lab in the sense that you will learn about cache coherence protocols. Okay, improving the protocol is extra credit, but I don't know who will do it. We'll see. There was one very interesting extra credit for lab 6 that I will talk about. Final exam, we'll get to it. Let's cover this in the next class in more detail. Lab 6 grades. This is the distribution for those who submitted, actually. There were 37 of you who submitted. Some of you did not submit, and I'll propose a way of rectifying that, hopefully. But this was the top possible score, maximum possible, 2595. Chris has this, I guess you guys have this grading scheme for some reason that never adds up to something. I wouldn't call it reasonable. I guess that everything could be arbitrary, right? There's no point in making it 2500, if you will. But anyway, there are 7 of you who are very close. There were 5 perfect scores, which I will recognize soon. But this distribution was a little bit wider than previous labs. Is it because you didn't have time?
Yeah, it's pretty difficult to debug.
It's pretty difficult to debug? Yes.
I matched all the simulator, like the time you gave us, but then when I actually got the grade back, I was off for like 2 cycles on all of them, so it sort of took.
Oh, okay.
So it took me down like significantly.
Okay. Well, you can probably talk with Chris in terms of the grading. If you're just off by 2 cycles, then it may not be. I don't think it shouldn't take you down significantly, right? But you can talk with Chris offline. Okay. I'll propose. I'll give you another chance to actually attempt lab 6 for those of you who would like to improve. And I'll tell you about that. But before that, I'd like to talk about the honors for lab 6. Jason, who's sitting in the back, actually did a strike prefetcher for data cache misses and a next line prefetcher for I cache misses, which makes sense, I think, a next line prefetcher for I cache misses, right? As we've covered, because it's likely that you're going to prefetch the next line after you fetch this current line. And that's where he is, because we gave him 15% extra credit for that. And these are the ones who actually completed the lab with full credit. So all of the tests were passed and they matched. So you can be one of those. I'll give you another chance for lab 6. I know it's a difficult time of the semester, but I would like you to learn. In fact, this exercise that we're having you go through is not meaningless, because this is what really happens when you design a processor. When you design a processor, you start with a spec, and you design a simulator that implements that spec. And at some point, you actually have the hardware. And at that point, you correlate your simulator with the hardware to ensure that your cycle counts match exactly, if you will, or the Verilog model. You have different simulators. So matching these cycle counts with some spec, be that spec be the hardware or some other golden simulator, if you will, golden model, is done very frequently in industry today. That's how you actually design processors. That's how you make your simulators better. That's how you design your next processor better in a better way. So in that sense, the exercise you're doing is important, very important actually. Like architects in industry try to correlate their simulators to real models in hardware to ensure that the simulators are correct. Yes?
Yeah, so you don't have reference cycle counts. How do you debug?
You do have reference cycle counts, right? Maybe you don't have everything, that's right. But that's part of the difficulty of the lab. That's like when you design a processor, you kind of know what your reference cycle counts should be, right? Now, if you have the real hardware, then it's a little bit easier. But then you still need to debug. You still need to ensure that your cycle counts match. You still need to find out what is the part that is missing on your own. So in this case, I think it's an important exercise for you to go through. So we'll give you another chance. For lab 6, we released the binary for the golden solution, which means that you can run any program as you wish, including the programs we will release or we have already released, and figure out cycle by cycle what happens. And you can debug your lab. You can turn in lab 6 by May 6th at the same time. Basically, the same policy applies. It's really due May 4th. You can use 2 additional days without any penalty again. And once you turn in, we'll grade your lab, and we'll multiply your grade by 0.8. Is that fair? Which means that you can get a maximum of 80% of what the lab is worth. But you will still get a correct lab, if you will. Hopefully. Does that make sense? So and this doesn't count off from your late days or anything. From now on, the late days don't count, if you will, because we've changed the policy this way. Okay? I'd like to make it a little bit easier on you since this is the end of the semester. But it's important for your learning also. Okay. Well, did I have anything here? And one more thing, since it's the end of the semester. If you're really crunched for time, don't lose the bigger sight of what's happening in the course. You're not here for grades anyway, I know, but if you're really in the position to care, plan wisely. Labs, 30%. We have 7 of them. Final exam, 30%. We have 1 of it. Amdahl's law. Right? Okay. You will definitely learn a lot from lab 7, but it will also take time. Okay? So plan wisely. You're all adults. And you know Amdahl's law very well by now. You know the bottlenecks in Amdahl's law. So plan wisely. Well, speaking of which, that was what we covered in the last lecture. Partly, right? Bottlenecks in parallel processing, at least parallel portion. Okay, any questions on the labs? Lab 6 and Lab 7 grading policy? You should refer to these slides. We will put these up. So if you have any questions, let us know. Okay. Last lecture, very brief overview. Hopefully you know about sequential consistency. Now, memory ordering, why it makes sense. You don't need to know about how it's actually implemented because we did not talk about it. But you can think about how it's implemented. It's actually, it could be difficult to implement if you want to get very high performance. We talked about cache coherence. We talked about whose responsibility it is, hardware versus software. And we've kind of came to the conclusion that if you want to design a general purpose processing system that's programmable by sane people, hardware is probably a better solution. It makes microarchitects' life complicated, but the programmer doesn't need to deal with whether or not a cached copy exists in multiple different processors' caches. Right? We talked about different methods of doing cache coherence, update versus invalidate protocols, and we spent some time in terms of the trade-offs. And we talked about, well, this is update versus invalidate can be applied to 2 big methods of doing coherence, Snoopy cache versus directory-based cache coherence. Well, either of these could be update versus invalidate based, right? Okay, today we'll wrap up cache coherence, and I kind of reordered this as a stale slide, and hopefully go into interconnection networks because it ties nicely with cache coherence. Remember, Snoopy cache works nicely with a bus, but bus is not scalable. On the other hand, directory methods do not require a single serialization point for everything, if you will. They do require a single serialization point for each cache block, but they're more explicit. And they don't require the bus, because caches do not snoop in this case. Now caches send explicit requests to the directory saying, I want this block, which is more scalable. But what other kind of interconnection networks can be designed to make the system more scalable in general? We'll talk about that. And probably we'll get back to more caching issues. So we'll do some out-of-order execution. OK. A little bit more on cache coherence because I rushed toward the end. I would like to go over this in a little bit more detail, the protocol trade-offs. There are two basic cache coherent methods. One is the Snoopy bus or Snoopy cache. It's essentially a bus-based protocol. It has a single point of serialization for all requests. And caches basically observe what's happening in the bus and act accordingly. Right? And we'll get back to that. Directory, on the other hand, it's more explicit. There's a single point of serialization per block, not for all requests. And processors make explicit requests for blocks, and this directory tracks ownership of the block. Remember, the directory has 1 bit for each processor, saying for each block, the directory has 1 bit per processor, saying whether that block is currently in the cache of that processor or not. Right? And if someone requests that block for reading or writing, now the directory knows where else in the system this block exists and can act accordingly. Right? Instead of caches making the decisions on their own by observing what's every other action coming from every other processor in the Snoopy cache or Snoopy bus, here the directory gets requests for each block and handles coherence accordingly. Okay? So Snoopy cache coherence, we've given you the idea. All caches snoop all other caches read-write requests and keep the cache block coherent. Easy to implement if all caches share a bus. And I've covered all of this, so you remember this, hopefully. Keep this question in mind. Each cache broadcasts its read-write operations on the bus. What if you would like to have a 1,000-node multiprocessor? Right? In that case, do you still have a single bus? We will get back to this toward the end of the lecture after we finish coherence. So this was the Snoopy cache. Basically, what do you need for a Snoopy cache? Basically, each block in a cache can be in different states. Right? And those states are modified as the cache observes actions that are happening on the shared bus coming from other caches, and as it observes actions that are happening from its own processor. So what can the processor do? Processor can have two actions to a block. It can read the block, it can write to the block. Processor read, processor write. Bus actions to the block could be read for the block or write for the block. These are coming from another processor, right, through broadcast. Bus write can also be called bus read exclusive. They're not exactly the same thing. You can have a bus write and also a bus read exclusive, separate signals. Why? Because you might actually want to read the block as exclusively, even if you are not writing to it at this point in time, right? In fact, several processors have this write hint instructions, if you will, to bring the cache block early before they actually write to them. Alpha, for example, has a write hint instruction. The compiler can insert this instruction before a write to a shared block happens, so that the coherence mechanism transfers the block before the write actually happens. Right? It's like a prefetch, if you will. Right? Does that make sense? It's prefetch for a shared cache block. So in that case, these two can be different. But let's assume that they're the same right now, bus write and bus write exclusive. Okay, simple coherence protocol, we've seen this, right? Valid versus invalid. And we figured out there was a problem with it, and we've talked about it, so I will not get into that in more detail. So we have a more sophisticated protocol, MSI, modified shared invalid. We have covered this in a little bit detail as well. So the idea is when a processor misses on the block, it makes a read request on the bus. This is, let me draw this so that we can follow this more easily. Processor, cache. There are two: processor read, processor write. And then there are actions that are here: bus read, bus write. These are the observable signals from each cache. When a processor does a processor read to this cache, in an MSI protocol, what happens is, if the block is not here, is an invalid state here, a bus read is sent. Actually, let's do this. Yeah. A bus read is sent. So when a processor read happens on an invalid state to a cache block, a bus read is sent off the bus, and the block is brought in shared state. Right. So it could come from another processor's cache. It could come from memory. Let's say that no other processor has it. The block comes in shared state, right? Now the processor can do reads to it and writes to it, right? This is the MSI protocol. Let's say the processor does a read to it in shared state. It can do as many reads as possible. Shared state means that the block is present in several potential caches, right? It could be in one cache or it could be in many caches, but the block is not modified. It's clean with respect to memory. Make sense? Now let's see what happens if the processor wants to write to the block. If the processor wants to write to the block, it needs to transition from shared state to modified state. So it sends out a bus read exclusive signal, if you will, or bus write signal, let's call it. It's the same thing here. And this bus write signal, when another processor that has the block in shared state receives a bus read exclusive signal, if you will, it goes to invalid state. So this is the invalidation-based protocol. The processor now can write to the block and change it to the modified state. Modified means this copy is modified versus memory. It's the only up-to-date copy in the system. So it's modified exclusive, if you will, exclusive to this cache. Does that make sense? I'm not going to go through the protocol in detail because it's relatively simple. We discussed this. But do you see any problem with this? Yes?
You don't have the exclusive state, so when you bring it in, it'll first have to come in the shared state, and then when you want to write, you'll have to send out the bus readx.
That's right, yeah. Yes. So let's say this processor has the only copy of this cache block in the system. What happens is it needs to still send an invalidate signal. So this shared state means that at least one processor has this block in its cache. That's the only knowledge that the processor has. So if the processor wants to write to the block, it doesn't know if this is the only copy in the system or if some other processor has the copy. So it has to send out an invalidate signal. But that may not be good. So the problem is, let me restate it. A block is, to begin with, there's no block in any cache. When I read, the block immediately goes to the shared state, although it may be the only copy that is cached. Right? No other processor may actually ever cache that block. Why is this a problem? Because suppose the cache that read the block wants to write to it at some point. Now it doesn't know if this block is the only copy in the system, or if some other cache has the copy. So it needs to broadcast and invalidate, even though it has the only copy. The problem is it doesn't know it has the only cached copy. So if the cache actually knew it had the only copy in the system, it could have written to the block without notifying anyone, thereby saving this valuable bus bandwidth, if you will. So that's the idea of MESI, the solution. And the idea is simple: add another state indicating that this is the only cached copy and it's clean. Right? And that's the exclusive state. So when you, it adds a little bit more complexity, of course, because you need to figure out when you read whether or not the block is the only copy, right? So how do you do that? Basically, when the processor does a processor read and it misses in the cache, it sends out a bus read. During this bus read, all of the caches respond saying whether or not they have the block in the system, right? In their own data store. And if no cache has the block, which can be detected by a wired or signal on the bus, and a cache asserts that signal if it has the copy. If this wired or evaluates to false, then this cache knows that no other cache has the copy. Right? Then it can go into the exclusive state. Right? Make sense? So there is a little bit hardware complexity, but now what it enables it is if the cache knows that the block is an exclusive state, it can write to it without notifying anyone. Right? So that's the advantage. This is also called the Illinois protocol, and I haven't assigned this paper, but I would recommend you reading this paper. It was developed at Illinois, that's why it's called the Illinois protocol. But Papamarcos and Patel paper very clearly explains what was the state of the art in the 80s and why they designed this protocol. You don't need to read the evaluation parts of the paper. The first 2 pages or 3 pages are really enough to understand this very clearly. So if you want to know more about it, you can read that paper. So that's the idea of the MESI protocol. And I have some more detail here. You can actually add other signals. And this. So what are the states, first of all? There are 4 states, modified. Modified means that the cache has the exclusive copy, and it's modified. And we'll get back to that too. Exclusive state, this is the state we added. The cache has the exclusive only copy in the system, and it's clean. Shared means at least one cache has the copy, and it's clean, right? Invalid means, well, the cache doesn't have the copy, right? So this state diagram, which I will not go through, but you can study on your own, I will go through the Pentium Pro state diagram a little bit, which I rushed through last time. But the state diagram is complete in the sense that it tells you what happens. Actually, maybe I will go through this part. So this is the state that I was talking about. When you get a processor read to a cache block, you can go into either the exclusive clean state, this is the E exclusive state, or you can go to the shared clean state. And that depends on whether only this processor has requested the cache block or whether or not some other cache actually has the cache block based on that wired or signal that I talked about, right? So if this processor is the only processor that has the cache block, then it goes to the exclusive state. Otherwise, the block goes into the shared state. Okay? And other caches also act accordingly, right? This is local to each cache, if you will. Yes?
Would another advantage of having the exclusive state be that when you evict a block, you might not necessarily need to write, like, propagate the write to like low or America. Because if it's clean, then you don't need to change it.
Well, if the block is clean, you don't need to write it anyway, right? If you actually wrote to it, then you go into modified state.
But can you check that even in MSI? Because you only have you don't have a state that says it's exclusive and it's clean, right?
Yes, but if in MSI, if you write to a block, you go to the modified state, right? If you're in the shared state, you don't need to write back the block, right? If the block is never written to, if the block is never modified, you don't need to write it back. Okay. Okay. So I've also given you 2 additional signals here. So bus invalidate. You can actually divide bus write into bus invalidate or bus read invalidate, if you will. Meaning, bus invalidate means invalidate the block, but you already have the data. So other processors do not need to supply it. And bus read invalidate means invalidate the data, but I also need the data for the cache block. That means other processors know to supply the block. And you can look at the state diagram to figure out when it's used. So this is the state machine that you will actually build in Lab 7. It's very similar. And hopefully you read the handout. And hopefully you'll enjoy doing it. Who has started Lab 7, by the way? Oh, that's good. Quite a few people. Based on Lab 6 hand-ins. I thought fewer people would start, but that's good. Okay, so this is implemented in Pentium Pro, and a lot of processors do this kind, implement a variant of MESI protocol, if you will, and we'll get to some variants soon. But here again, the same thing, right? In a processor read, if another cache has the data, you go into the shared clean state. If another cache doesn't have the data, you go into the exclusive state. And I guess I'll let you study this block, unless you have questions based on your studying so far. I don't want to go through this state diagram for the entire lecture, unless you want me to. Okay, good. People say no. If you want me to speak up now. Everything clear? Okay. You guys have done the state diagrams before, right? So it should be relatively easy. But yeah, this is the Pentium Pro state machine. Okay, so there are, of course, trade-offs associated with all of these protocols. For example, one trade-off, when you're in the modified state, and let's go back. When you're in the modified state, and someone else wants to read the block, should you go to the shared state, or should you go to the invalid state? Any ideas? There could be trade-offs related to this, right? So this is the modified state, and you get a bus read. Here, the state diagram says go to the shared state. But there is an implicit assumption that this processor will keep using that block. It may not be true. Maybe if you had better knowledge, you would go to invalid state. And if this processor is not going to use that block again, you would allocate that block to some other cache block coming into the same set, right? Yes?
I think you put in shared clean, but just don't update its LRU status, you're not losing anything.
Yeah, you could do that also. You could potentially do that as well, right? That's another thing. But, I mean, if you go into the, if you're in the modified state, and if you get a bus request, bus read, if you go to the invalid state, the other processor can go to the exclusive state potentially, right? Exclusive clean state if you write back to memory at the same time. So the other, you may eliminate and invalidate later on. So there's another potential advantage. That's if you think about the protocols in the future. And that makes the design of cache coherence protocols interesting, I think. Okay. But that, I mean, if you do something like this, it becomes more complex also, right? Okay, so another trade-off, cache-to-cache transfer. On a bus read, should the data come from another cache or memory? Right. If you send the data from another cache, this may be faster, especially if memory is slow or highly contended, right? If the data actually comes from memory, now this is simpler. Now, memory doesn't need to wait to see if the cache has the data first, right? Memory doesn't need to supply data. The protocol is simpler. And there's less contention at the other caches also, because the caches don't need to transfer data now. The downside is it requires write back to memory on a downgrade from the modified state, if you will. So in the modified state, and there's a bus read, if the data doesn't come from the cache, this data first needs to be written to memory and then sent back from memory to the cache, right? Make sense? Okay. So is this necessary? I guess let me get to the problem with MESI, if you will. Maybe it's not as big of a problem as when we moved from MSI to MESI. Shared state requires the data to be clean, right? If you look at this, we always said shared clean, and modified is always exclusive modified, right? So we don't have something called shared modified. Well, what does this mean? Shared state requires the data to be clean, which means that all caches that have the block have the up-to-date copy, and so does the memory. if you were going into the shared state. The problem is, if that's your definition of shared, you need to write the block to memory when bus read happens when the block is in modified state, right? Because one processor has modified data. You cannot just transfer that data to another processor and make it shared modified. You have to do shared clean, which means that if you go from, let's go back to the state, modified to shared, there's an implicit write to memory here, right? Because the shared means clean. Clean means up to date with respect to memory. Well, why is this a problem? It's a problem because memory can be updated unnecessarily, right? Which means that some other processor may write to the cache block while it's cached, or many processors may write to the cache block while it's cached. But when you're transitioning from modified state to shared clean state, you're always writing the block back to memory. Right? So you're wasting valuable memory bandwidth again. So you can actually solve this problem. Oh, that looks bad, huh? Okay, there are two ways of solving this problem. First of all, one thing you could do is do not transition from modified to shared on a bus read, right? You change the protocol. When you're in modified state, remember, modified is modified. The block is modified and it's the only copy in the system, exclusive. And we have shared. Shared means that the block is shared and it's a clean copy. If you go from here to here, when you observe a bus read, you need to write back the block to memory. But the idea is, don't do this. When you get a bus read in modified state, instead, invalidate the block and supply the block to the processor that actually wants it, right? In fact, if that happens, then the processor that actually wants the block can go into the modified state directly. Now, there may be issues with it, but that's the high-level idea, right? The other processor can go directly into the modified state. The block is modified in, so let's see what's happening. Processor 1, cache 1, processor 2, cache 2. This processor has the block in modified state. Now this processor wants the block. It sends a bus read signal. When this processor observes a bus read signal, it sends the block to this processor and invalidates the block. Now this processor has the block in modified state. Of course, you need to ensure that there enough data is, enough information is communicated such that this processor caches the data in modified state, right? That way you don't need to write back the block to memory. You've saved memory bandwidth. And if this processor is not going to do anything with that block, it's good. And if this processor is going to, well, it's requesting it, so it's going to do something with the block, hopefully, right? Now this processor can write back the block if it's going to be evicted, right? So this saves the memory bandwidth in that transition. It's a different protocol. Yes?
It seems like it can also create a lot more bandwidth going between the caches, though, because like if processor 1 reads, then processor 2 reads, then processor 1 reads, etc. It keeps moving between them.
That's right. So it depends on the communication pattern again. All of these things, the protocol really depends on the communication pattern. What if it was something like this? This processor was the producer and this was the consumer. So let's say at the programming level, what is really happening is processor 1 is executing a thread that produces values that processor 2 is reading. And this is the right thing to do, right? Processor 1 is writing to the cache blocks. Processor 2 is reading from the cache blocks. This processor will not write to those cache blocks again. In fact, there's a name for this. It's producer-consumer, or pipeline parallelism, if you will. You set up the threads such that thread 1 does something, gets some input data, does something to that data, and inserts the data, modified data, into the queue. Thread 2 picks it up, does something to it, inserts it into another queue. Thread 3 picks it up, does something to it, inserts into another queue, right? And if these threads are executing on different processors, now that may be the right thing to do, right? That protocol may work well, right? Because this thread is going to write to a cache block. It'll become modified in its cache. This thread is going to send a bus read request to get that cache block. Now this thread doesn't need that cache block. It can invalidate it. And this thread now is going to use that cache block and write to another cache block, which the other thread is going to read. Does that make sense? Of course, if your communication pattern may be much different from this, then this protocol may not work. So I guess one challenge is how to identify how your protocol should be designed based on your communication pattern. Okay, that was one idea. I'm giving you these ideas just to show that there are actually trade-offs involved in all of these decisions, right? And this may not be the best thing to do for all possible cases, but in this case, it would work nicely, right? Actually, this kind of pipeline is very common in graphics or image processing applications. You take an image, you do something, one thread does something to it, another thread does something else to it, like filtering. You do something else to the image, maybe you zoom into it, maybe another thread does something else to it, and eventually you get a product, right? Video processing, for example. Okay, the second idea, well, remember what we were trying to do is not to write to memory when we don't, not to update memory unnecessarily when you get a bus read transaction in the modified state, right? That was one solution. The other solution is to actually transition from, the other solution is basically redefine what shared means. Shared doesn't mean clean anymore. Shared means modified as well, potentially, right? So transition from modified to shared, but designate one cache as the owner, who will eventually write the block when it's evicted, right? Now this complicates the protocol a little bit. Now shared means shared and potentially dirty, right? And owner means, oh, it's dirty, and when I evict this block, I'm going to write it back. And of course, you need to perhaps have some other actions in this case, because you don't want other processors to write back the block also, right? Okay, so this is a version of the Moesi protocol. You could hear this acronym as well. So there's another state, owner state, if you will, that the cache has, and the cache knows that it's going to write the block when it evicts the block. Make sense? So this way you eliminate that write back to memory when you go from modified to shared. Because shared doesn't mean clean anymore. It means potentially dirty, right? So I'm sure you can come up with other issues related to these protocols, and you can add more states, if you will. The protocol basically can be optimized with more states and perhaps prediction mechanisms, right? Perhaps you predict that this is happening. Predict that whenever this processor, or whenever processors write to blocks, they're done with the blocks, right? You can have prediction mechanisms that predict that case and go to different states based on the predictor design. This way you can reduce unnecessary invalidates and unnecessary transfers of blocks between caches and memory, and invalidates on the bus. The downside is there's a trade-off. More states and optimizations. Well, first, usually they provide diminishing returns. Going from MSI to MESI was a big step, if you will. Going from MESI to Moesi is not as big of a step. Depending on the workload, on average, doesn't provide as much performance as going from MSI to MESI. Going from Moesi to your favorite protocol that you might want to do for Lab 7, I don't know. Maybe it's also a diminishing return, unless you find something that's missing in a fundamental way in all of these protocols. The second thing is they're more difficult to design and verify. In fact, we did not talk about potentially corner cases in a lot of these protocols, but you need to ensure that they're correct, right? Now, correctness is easier if you have a bus. In this case, if Snoopy caches, correctness is easier to maintain. But even then, there are conditions. I think when my TAs designed the lab, for example, they tried to make it as easy on you as possible so that we minimize those potential race conditions because requests complete at different times, right? So you need to make sure that the state transitions happen at the correct time. So those race conditions need to be handled correctly. And as you have more states, as you have more sophisticated protocols, prediction mechanisms, those become harder to handle. Okay? Okay, did I skip a slide here? Maybe. Yeah, well, you can read this. Now you can go back and read and understand what that means. Okay. So revisiting the high level, let's go back to Snoopy cache and directory, and then we'll cover directory a little bit more. These were the two major methods, and we've covered Snoopy cache in detail, right? And these protocols are all easier to implement on the Snoopy cache because you have a single point of serialization for everything, if you will. So what are the trade-offs? Snoopy cache, you don't need to explicitly request to a directory, right? Critical path of a request is short, if you will. It's just a bus transaction where every processor is aware of what's going on. Right? Whereas directory, remember, you go to the, first you send a message to the directory asking for a copy. And the directory figures out where things are and sends you back the block, right? Whereas here, you don't need to go to the directory. One level of indirection eliminated. It's easier to implement because bus provides you global serialization, right? Arbitration is easy. It's simple, again. If you have a bus-based unit processor, you can adapt that to accomplish this. Okay. The downside is it relies on broadcast messages to be seen by all caches, right? Why is this bad? Well, that nice abstraction to make it easy to implement also makes it not scalable because now you have a single point of serialization, right? And again, if you want to put 1,000 processors on the bus, good luck. Directory, the downside, I already told you, it adds indirection to the critical path of the request. When you get a cache miss, you first go to the directory and then go to memory or some other cache. It requires extra storage space to track the share sets. Now it's true that bus-based protocols, the Snoopy cache, also require states, but these are per cache block, right? For each cache block, you need n number of bits. Whereas directory, for each cache block in memory, you need to track who has that block in its cache, right? So this is much bigger. If a block is not cached, you don't need these states in a Snoopy cache protocol, right? If the block is in no cache, then you don't need to keep track of it. Whereas directory needs to keep track of every block in memory, if you will. And we will get back to this in a little bit. This can be approximate, right? As long as you maintain correctness, it's fine. And we've already seen one way of representing set membership, if you will, while maintaining correctness. Bloom filters. You already seen it on the exam also, right? So you could represent which caches have this block using a Bloom filter, right? Of course, now protocol becomes a little bit complicated in terms of modified. You need to keep track of who actually has the modified copy. But we knew that. We already kept track of that, right? Somehow. Okay, so false positives are okay. Protocols and race conditions are more complex, and we will see a couple of examples of this. I will not go into detail, but hopefully if you guys take 742, there will be more on this. The big advantage, I've given you all of these disadvantages, so why implement this thing, right? The big advantage is it's more scalable, right? If you want to design a system with 1,000 or 10,000 nodes, multiprocessors, then you just design a scalable interconnect, and you distribute your directory, if you will, and design a directory protocol that communicates, that doesn't require broadcast, right, of messages to be seen by every processor. Right? It's scalable. Why is it scalable? Because of this exact indirection, it's scalable. Right? You don't say, I want this block, everybody else in the world, no. You say, the directory node that actually serves as a serialization point for this block, please give me this block. I don't care how you do it, but I would like this block. That indirection makes the protocol scalable. Okay, so let's revisit this directory-based cache coherence. I'll go over the. I won't go over this. This is the idea of a directory, an example mechanism. And remember, this is, if you can read my handwriting, this is a very simple directory, right? This is, for each block, you have p plus 1 bits, where p is the processors, and 1 bit says whether anyone has it in an exclusive state. So you need this. Okay, I'll let you look at these slides. So do you really want, first question is, do you really want p plus 1 bits? Can you represent this in another way? This is another way of looking at the protocol. For each block in memory, you keep track of whether the block is shared and which processors share it. These are the bits set for processor 0, 1, 2. And whether the block is an exclusive state. So processor 2 has it and it has an exclusive state. So basically, key operation to support in a directory is the set inclusion test, right? Whether you actually have that block, which processors have the block. Again, false positives are okay. It's okay for the directory to think, if you will, that a processor that doesn't have the block to have the block. If a processor may not have the block, but the directory, it may be okay for the directory to think that it has the block. Right? In that case, what happens? If another processor requests the block to write, let's say you have a read exclusive request, another processor wants to write to the block, let's say to block 0. And let's say processor 2 actually doesn't have the block. The directory, upon receiving this read exclusive request, it sends invalidate request to processor 0, processor 1, processor 2. Saying invalidate the block that you have or you may have. And processor 0, 1, 2, processor 0 checks its cache. Oh, the block is in its cache, it invalidates. Processor 1 checks its cache, the block is in its cache, it invalidates. Processor 2 checks its cache, the block is not in its cache, and it doesn't do anything, right? So it's correct still. And remember, we also required acknowledgement such that so that the directory knows that all of the caches are invalidated, so they're not going to use the data. In that case, processor 0, after invalidating its block in the cache, sends an acknowledgement saying that, oh, directory, I've invalidated the block. Processor 2, it didn't have its cache, but you've designed the system. Processor 2 can infer that the directory just made a mistake, right? It sent a message saying invalidate. So processor 2 goes along, if you will, says, I am acknowledging your invalidate, right? So that way you can reduce the number of bits that are required to keep track of which cache has this block. And there are multiple ways of doing this. You can have linked lists, you can have other compressed representations. Bloom filters are probably much more interesting in terms of representing them. Okay, so you don't need to have the full bit vector. Of course, there are, again, trade-offs, right? If you don't have the full bit vector, now you're sending extra invalidate messages. Okay. Okay, basic operations. I've already shown you this. Let's take a look at some pictorial examples, if you will. Let's say processor 0. Processor 0 wants to read a cache block. What it needs to do is first send a read request to the directory node that's home to that cache block. And remember, in the last lecture, we talked about distributing the directory. You can actually not have a single location for the directory, but different nodes can have different portions of the directory, and some bits in the physical address can determine which directory node is home to that particular cache block, right? And every node in the system knows which bits, so if you get a physical address of a cache block, this is the physical address. This is the block offset, if you will, cache block offset. And let's say you have, let's say 32 home nodes that over which your directory is distributed on, these 5 bits here determine what is the home node, if you will, what is the directory that contains information about this cache block. Right? So it's simple. So this processor 0 sends a read request, and the home node responds with a response. If this is the only processor that has read it, it can send an exclusive copy, or it can send a shared copy. Or it could be this way, right? It could be if the data is shared, if another processor has the copy, the home node can say, tell processor 1, send this block to processor 0, right? So there's a lot of flexibility in the design of the protocol, if you will. Okay, let's take a look at another case. Processor 0 wants to write to the block. Let's say it sends a read exclusive request to the directory. Now directory sees that some other processor, processor 1 let's say, has the block, so it sends an invalidate request to that processor. This processor acknowledges, if you will, that request, saying that, oh, I've invalidated my block, and here's the new copy, if you will. This processor may have the block in modified state, right? And it may also do this, right? If your protocol is scalable like this, you could decide, while sending back the modified block to the home node, to the directory, also this message can contain information saying that invalidate your block and send it back to me, and also, by the way, send it to the processor that requested it, right? Processor 0. Does that make sense? So that's the nice thing about a directory, if you will. And if you have a scalable interconnect, of course, if you have multiple paths between these different processors, you can send the owner, the previous cache or the previous processor that had the block in modified state can send it to the directory as well as processor 0, and this could go through different paths, right? And in fact, this could go faster than this, depending on how close these nodes are. Right? Okay, so another example, if you will. This could get very complicated also. You need to ensure that things work. Let's say both processors want to read the block in an exclusive way. They both want to write it, and directory receives those requests at the same time. What do you do, right? Well, the directory can only give the block to only one of them, right? It says basically, processor 0, you're granted the right, and too bad, processor 1, retry later. That could be one way, right? This is called a NAC, Negative Acknowledgement. Now processor 0 has the block, it's happy. These are Chris's slides, by the way. So if you're wondering if I would put something like this on my slide, it's not mine, it's Chris's. So this processor comes unhappy, if you will. And it retries, right? Later, at some point, it sends a read exclusive request. Now the directory sends an invalidate request to processor 0 that had the block, right? So it needs to keep track of which block which processor has it. And this invalidate request, again, can be similar, right? The processor 0 sends back the block to home, as well as it sends it to processor 1. Now that processor is happy. But you could see that this kind of protocol can actually lead to some fairness issues, right? When two processors request the block, then who do you actually grant it to? Well, actually, which requester should be preferred in a conflict, right? And I will not go into this, but there could be ways of handling it. Basically, who do you send back the request to? One solution is actually not NAC the requests, but queue the requests, right? The directory can have a queue of requests. Basically, whenever it receives these two read exclusive requests, initially, let's go back to the beginning. When both processors send the read exclusive request, instead of granting, well, it needs to grant one, but instead of NACing the request and saying retry processor 1, it can queue all of those requests and service them in that order, right? That way, maybe you can eliminate some fairness issues as well, because now the directory sees all of the requests to that particular cache block, right? And it can, or you could have a protocol that's a combination of both, right? What if, so the problem with queuing the request is what happens when the queue gets full, right? When the queue gets full, you probably want to NAC at that point, right? Well, what is your other option? I don't know if you can do something other than NACing. Okay? So this is something for you to think about. We're not going to cover this, but directory-based protocols have these issues that you need to think about. These issues did not exist with a simple Snoopy bus, right? But if you want to scale the system, you need to deal with these issues. You need to guarantee that nodes will make forward progress. Well, you can ask, why is this happening, right? Why are all these processors wanting to write to the block at the same time? There are higher level solutions to this. This is called ping-ponging, if you will. I'll throw another terminology at you, ping-ponging. The idea is, it's not specific to the directory protocols. You have processors with caches, and processors write to the blocks, and blocks need to be transferred and invalidated between different caches. And if this happens too much, this could actually saturate your bandwidth on the interconnect, right? Especially what you don't want to happen is this processor writing to a block, another processor invalidating it, writing to it, and this processor needing that block again and writing to it. That kind of ping-ponging you would like to eliminate at the higher levels. And if you design your software and share data structures better, you can do better. But I will not go into that in this class at least. Okay? Any questions?
Why do you send the data back to the directory?
Oh, again, that's a design choice, right? You don't have to necessarily. You can design a protocol that doesn't, exactly. You can design a protocol that doesn't send the data back here, and the directory still keeps the state. It's the same design choice, if you will. Do you write it back to memory, or do you directly send it to the new cache that requests a copy? Okay. In fact, that brings up a good point also. You could have the same MESI protocol, exactly the same states, if you will. Maybe you don't keep track of the states exactly the same way you would do. But that could be implemented as part of a Snoopy cache or as part of a directory, right? It's just the operations that need to be performed would be different, right? Okay. So now that we talked about scalability of the system, it's important to talk about what enables a system to be scalable, right? And that's really the interconnect. We talked about bus implicitly, but bus is not the only way to connect systems. When I say interconnect, this is basically the substrate, if you will, the wires that are used to connect components. And there are many examples of this. In this case, I abstract as a cloud. You can connect processors to processors, processors to memory banks, processors to caches, caches to caches, and processors to I/O devices. Right? It's essentially a network, if you will. And all of these, today not many people have laptops. Looks like laptops are concentrated on that side. But they're part of the interconnection network, right? So why is it important? This part is an important part of the system as well, but why is it important? Because it does affect the scalability of the system. How large of a system can you build is really dependent on how you can connect these components in a scalable way, and also how easily can you add more processors, right? Depending on your interconnect, you may or may not be able to add just another processor into your system, right? It also affects your performance and energy efficiency. How fast can processors, caches, and memory communicate? How long are the latencies to memory? Right? So there are three major properties, if you will, of an interconnection network, which we will cover mainly the topology part, although we will touch upon some of these other ones as well. Topology specifies the way switches are wired, if you will. Switches are things that are required to connect the different components. And bus is one topology. Bus says there is only a single wire, if you will, at an abstraction level, and all processors are connected to it, right? And there's arbitration that happens to ensure that only one component has control of the bus at any given time. So this affects a lot of things, of course: routing, reliability, throughput, latency, and building ease. And we will take a look at some of the different topologies in the rest of this lecture. The second is routing algorithm or routing strategy. How does a message get from source to destination? Right. Do you set the path dynamically or statically? Right. Actually, there are many choices here. You can ignore this part. But when you generate a message, do you know how it will go at that point? Or do you set up the path before you send the message? Do you do circuit switching? Or do you do packet switching? You send the message, forget about it, and somehow the nodes that receive the message, intermediate, they know how to route the message to its destination. That's how internet works, right? It's a packet switch network, if you will. When you send a message to a server, to Google, let's say. Google's a favorite example because a lot of people send messages to Google. The message goes from your computer through the TCP/IP stack to another computer. And another computer decides to send it to another computer. And that route is determined dynamically, right? A packet is switched between different nodes. Similarly, when you design a multiprocessor, do you design a system that way, packet switched? Or do you first set up a path, send a control packet saying, I'm going to send a message from this computer to Google. Now, all of the computers, I'm going to send, I don't know, 1 million bytes, let's say. For the next 1 million bytes, send me a route. Or let's set up this route. That way, you set up a circuit, if you will, and all of the messages go through that route. Does that make sense? Okay. We'll get back to this, but we won't cover a lot of details of it. You can actually, if you have taken a networking course, you would have seen this already. We'll cover it as it relates to multiprocessor design. Buffering and flow control is also important. So what do we store within the network? And do we actually store anything within the network? How do we ensure that the network doesn't get oversubscribed? How do we resolve contention, if you will, when two packets need the same link? How do we arbitrate between them, right? In bus, well, you have one link, right? So there needs to be some arbitration, and that arbitration needs to be fair, right? We didn't discuss this, but there needs to be some fairness in that arbitration also. Okay. Let's take a look at some of the topology design choices. So these are actually all interesting topics and require much more than a single lecture or whatever remains of a lecture at this point to discuss. And if you're interested, you can certainly take the parallel architecture course. In this course, we will cover mainly topology. And these are some different topologies that people have developed over time, if you will. I'll let you look at that quickly. But these topologies differ in terms of their cost, latency, in terms of the number of hops it takes to send a message to another processor or another cache, and in terms of contention, like how much is the network saturated, if you will. Saturated meaning, is the network always utilized? I'm not going to exact metrics, but and there are many metrics exist that you should think about: energy, bandwidth, overall system performance, and your topology affects all of these. Let's take a look at some of these topologies. Well, bus you already know, right? This is an abstraction, if you will. You have 8 caches or processors, and they're all connected to this bus in this case. And this is the example that we've been looking at. Well, somewhere here, yes. You have processor, cache, and there's a bus. This is our Snoopy bus, right? If you will. It's nice, it's simple, it's cost effective for a small number of nodes. It's the simplest topology you can have, I think. Maybe you can challenge that. I don't know. It's easy to, the nice thing about this is it's easy to implement coherence, right? You can have Snoopy caches, and it gives you a serialization point for every single request. In fact, it does make sequential consistency also easier. But the downside is not scalable to a large number of nodes, right? As you add more nodes here, there are two issues. As you add more nodes, you increase the electrical loading, which means that you cannot run your bus at a higher frequency, right? If you have 10,000 nodes, this bus will run like a dog. That's one thing. The other thing is, as you add more nodes, presumably they're going to send more requests, right? But you have only limited bandwidth here. So your bandwidth saturates faster, right? Your contention increases as you add more nodes. These are two different issues, but they both affect your scalability. As you add more nodes, your frequency reduces, which means that the maximum bandwidth you can support reduces. As you add more nodes, you need more bandwidth, right? Because presumably these nodes will communicate, except you cannot get that. The other issue, well, that's the second part. The other issue is it's a single point where everybody communicates, right? If there's local communication, let's say this processor only needs to get data from this other processor's cache somehow. You design a protocol. Whereas this processor only needs to get data from this other processor's cache. In a directory-based protocol, it's possible, right? They may not need to communicate with each other, with the entire system that much. But while these two processors, but there's only one communication that happens at any given time, right? You cannot have these two processors communicating at the same time these two processors are communicating. Right? So that also affects your scalability because it's a single point. So how can you solve this problem? At the other extreme, you have the point-to-point communication interconnect. In which case, every node is connected to every other, right? I think you can challenge this perhaps also, but this is the most expensive system you can build in terms of interconnect. So node 0 is connected to every other node. Node 1 is connected to every other node. Node 2, node 3, node 4, node 5, node 6, and 7. I guess 7 already gets connected. That means you connect everything else to it. And these are bidirectional links. That's the assumption. The contention is the lowest here, right? When node 7 wants to send a message to node 2, it's great. It has an exclusive link, if you will, to that node. And potentially this could be lowest latency also because of contention. So this is ideal, if you will, if cost is not an issue. But cost is always an issue whenever you design a system. An engineer is someone who can do for a dime what any fool can do for a dollar, right? So you can say cost is not an issue, but then an engineer will come and design a better network that gets better performance, and you're out of business soon. Okay, so the downside is its highest cost. Why? Well, ON square links. And perhaps you'll contrast this to the next topology that I will show you. There are no ON connections or ports per node, right? So each node needs to have n ports, if you will, where n is the number of nodes. Well, I guess n minus 1. But it's still ON, right? Order n. Okay? So it's not scalable because of this, really. So on the one hand, you have a very simple topology that's not scalable because it runs into contention issues. On the other hand, you have another topology that's not scalable because it runs into cost issues, right? So the question is, what is there in the middle? And the middle has a very big design space. Yes?
Also in this, how would you serialize something?
Yeah, so that's another issue that I did not talk about. But that's very good. Yeah, how do you serialize something? Well, what do you want to serialize? You could distribute your directory across all of these, right? If you don't need global serialization, then it's not that hard. But if what you mean is broadcast, then broadcast is hard, right? Yeah, you cannot broadcast a message. Basically, a broadcast is easy on a bus because Once you send the broadcast message, everybody sees it. Here you need to send individual messages to everyone. So the number of messages increases in this case if you want to broadcast. Okay? How do you lay out on chip? Let's say you implement a 1,000 core processor. How do you lay this out on a chip? That becomes a little bit hard also, right? Because although it looks regular, then how do you actually do these connections, right, on the chip? You don't have that many wiring metal layers, especially if you want to add 1,000, 10,000 cores. Okay, that's something to think about because today we're putting many processors, many cores on chip, and this is an important concern. Okay, so we decided this is not scalable. So can we get the benefits of something similar to this with reduced cost? And that's the idea of a crossbar. In a crossbar, still every node is connected to every other, except only one can be using that connection at any given time. So if two nodes need to connect to the same node, then you get serialization. But if two different nodes are connecting, two different pairs of nodes are connecting, then there's no serialization, right? It's not like the bus. This enables concurrent sends to non-conflicting destinations. So basically that's what this mux is, if you will. It represents if anybody wants to connect to node 0, if you will, they need to go through this mux. Whereas here, the difference is here, any node can connect to, can send messages to node 0 concurrently. Okay? So the advantage of this is still low latency and high throughput unless you're communicating, your destination is the same node. Even then, well, then it looks like kind of like a bus, right? The downside is it's expensive still. And it's still not scalable because the cost is O(n) square. If you look at these connections, it's n square, right? Switches. So cost, let me define this a little bit more clearly. How many switches do you need to connect? And what's a switch? Basically, a switch is something that decides where to send the packet. Here, you have a switch at each of these. Right? And actually, let me show you a better picture that gives you those switches in a simpler way. So when node 0 wants to send a message to this node, this switch is enabled, right? When node 5 wants to send a message to this 4, then this switch is enabled, right? So you have O(n) square switches. And when node 0 and 1 together want to send a message to, let's say, 2, then these two switches somehow, there needs to be some logic that enables only one of them, right? Okay, so I didn't show the control logic, obviously, here. Okay, so difficult to arbitrate as n increases. And again, that makes things slower, right? Let's say if you want to put 10,000 of these here and 10,000 of these here, essentially you have a bus, right? Or some arbitration mechanism is needed for the conflicting destination. But for small-scale systems, this has been used. This is used in some multi-core processors. We'll take a look at that. Sun Niagara 1, 2, IBM Power 5, and I think the later IBM processors also have this. They use it to connect the cores to cache banks, the shared cache banks. This is the design for the UltraSpark T2, if you will. So you have cores. Each core, this is the connection to bank 0, basically, from each core. And this is the muxes that I was talking about, right? So each core, well, yes. So this is the connection from the core to the different banks. And these are the connections from the cache banks to the cores. And this is the non-cacheable unit, if I remember correctly. So this is essentially the crossbar. It's not shown the same way I've shown it, but this shows the conflicting destination. If all of the cores want to send a message to bank 0, this is how arbitration is done. And that's the arbitration that they talk about. It's a 4-stage pipeline for arbitration, essentially. You request, arbitration happens, and arbiter selects one source, for bank 0 in this case, and the transmission happens. And when the cache needs to respond, again, a similar arbitration happens. If, let's say, core 0 requested both from bank 0 and bank 5, then both banks need to send the message, send the packet, send the data back to core 0. They need to arbitrate, right? So that's where a network like a Crossbar is useful. In this case, they have 8 cores and 8 cache banks, so it's not that many, right? Even then, this does consume power. If you look at the power numbers, power consumption numbers of these chips, this Crossbar does consume a lot of power because it has all the circuitry and it has all these connections. That's why this kind of Crossbar is not used in many other processors or other more cost-effective processors, if you will. Okay. So there are other ways of designing the Crossbar. This is a bufferless Crossbar, if you will. These are the switches, and you need to arbitrate for the switches. But you could make the bandwidth better in the Crossbar by adding buffering, right? You could also make the switching more flexible, if you will. What is the idea of buffering? Basically, add these buffers in the switches, in the routers, if you will. When a node sends a message, it actually doesn't directly send it to the destination node. It arbitrates somehow, but it can send the message to this buffer. Now you have simpler arbitration and scheduling because the arbitration needs to happen between these queues. And you can have efficient support for variable size packets, if you will. The downside is now you have n-square buffers, right? It's more expensive. Okay. So that's the Crossbar. Any questions? There are a lot of design trade-offs involved in this, even this also. I show you flow control here. Flow control means, what if the buffer is full, right? You'd better have some back pressure going to the node. This is a network interface. The node saying that, don't send me any more messages, right? So that needs to happen also. Okay, so can we get lower cost than a Crossbar, yet still have low contention? People have asked this question for a long time, and I'll give you the basic idea. The idea is multistage networks. Something like this, if you will. You have a network with multiple layers of switches, and the purpose of these switches is just to route the messages, if you will. So here, we had these switches. In a sense, this is a single stage, right? Node 0 wants to go to node 6, send a message to node 6. It basically enables a switch. That's it. There's no more switch after that, right? Multistage, the idea is add more switches in between. Where is this? Okay. So you have node 0, node 1. They're not directly connected to, I guess, memory. Let's say memory 0. The best way of thinking about these is memory, well, and P, let's say, memory X. Have layers of switching. And these intermediate nodes, the purpose is just to switch, just to route the data between nodes and memories. So if you look at this, this is an omega network. This is one way of designing the switches, and these are the nodes. And think about these as the memory banks. Now, these switches are essentially smaller crossbars, right? It's a 2x2 switch. Another 2x2, another 2x2, another 2x2. Make sense? And these are the last switch, that 2x2. So it's a 3-stage network. That's why it's called multi-stage. And you can obviously see that the cost is less, right? How many connections? Well, n log n. What is the latency? Well, now you have a multi-stage, right? So you need to traverse some number of hops. And you're not fully connected, if you will. You cannot, well, all nodes, in this case, I think, yeah, all nodes can go to all memory banks in this case. You can see, but there's less flexibility, right? Now you need to, if node 0 wants to communicate with this bank here, the message needs to go through this way, right? It goes through this output port of this switch, and then it goes through this output port of this switch. And there's more contention, right? What is that contention? Well, if 111 communicates with this bank, and at the same time, what's happening? Yeah, at the same time, 001 needs to communicate with some other node, if you will. There's contention in this switch, and potentially in this switch also. Right? That did not exist in the crossbar, right? In the crossbar, if two different pairs of nodes need to connect, they can connect without any contention, right? Here we've reduced the strength, if you will. We've divided the network into smaller crossbars. That's why you have more contention, right? Okay? So one question here is, do you do circuit switching or do you do packet switching in this case? Well, this is a circuit switch network. Basically, you somehow set up the route before, and you have more restrictions. Well, compared to crossbar, you have more restrictions, and it's more scalable. But this is one example. If you want to do packet switching, you don't need to arbitrate beforehand. You basically have buffers in each of these crossbars, right? And the arbitration happens locally. Does that make sense? Okay. Okay. So this is the difference between circuit switching and packet switching. Circuit switch, before you send the data, you set up the full path. If someone else is using that path, too bad, you wait, right? That's the difference here. For example, here, if you had circuit switching, let's say this node wants to send a message to this node, it sets up the path. Now this path is being used. This node cannot send a message to this node. Right? Whereas if you have packet switching, you're more flexible. Now decisions can be made more locally, if you will. Basically, you route each packet individually also, and I guess you can see the advantages and disadvantages over here. But let me see how much more time we have. Oh, we still have time. Okay. Basically, you establish the route and then send data. No one else can use those links. That's the circuit switching method. It's faster and higher bandwidth, if you will, because once you establish the path, you can just stream the data, right? And you can optimize the router switch, because the switch doesn't need to arbitrate for each packet, right? It just set up the path, if you will. You can think of this as reconfigurable logic a little bit, right? You reconfigured your muxes such that it sends the data to the right place early on. That's essentially what's going on. You're configuring your route early on before you send the message. That's why it's faster and higher bandwidth. But setting up and bringing down requires some protocol, right? Packet switching, on the other hand, routes per packet. For each packet, you send the packet. The next router now needs to make a decision. Do I choose this packet or that packet? Right. Now, already you have overhead in each router, right? A decision as to which packet to choose. Hardware overhead and latency overhead. The advantage is it's now you can route each packet individually, possibly via different paths, right? When you communicate, well, in this case, it may not be very clear because this is an omega network, but you can go through different paths to reach different locations, right? To reach the same destination. This will become more clear in some other networks that we will see. This is potentially slower because you must dynamically switch in each switch, and switch needs to make a decision, but no setup and bring down time. Okay, so before we move on, circuit and packet switching choice is actually independent of the topology, right? As we've seen, you could have a circuit switch network here, or a packet switch network, or you could have, well, we'll see other topologies. It's really a higher level protocol decision on how a message gets sent to a destination, right? However, some topologies are more amenable to circuit versus packet switching, and you can think about that. Okay, before we finish the multi-stage networks, not all multi-stage networks are as flexible, if you will. This is an example of a delta network. You can read this paper. This is also a nice paper. I'm not going to require any papers on interconnection networks. It'll be mainly on lectures, but if you're interested, it's an old paper that introduced this delta network. It doesn't support all possible permutations, and you can perhaps figure out how to get from each node to another node here. And this was the idea. The idea was to, again, replace costly crossbars as processor-to-memory interconnect. And you can have another example of an omega network. Right? And these networks were used in large-scale multiprocessors, previous multiprocessors. Today, they're a little bit less attractive on chip because what happens is you're essentially wasting your nodes as switches, right? Whereas you could have nodes over there. Right? These are the purpose of these nodes are essentially just to do the switching. Right? Okay. Any questions on multi-stage networks? Basically, the idea is you're adding indirection to reduce cost, right? You can think of it that way. Indirection. And these switches provide you indirection. Okay. Let's take a look at simpler topologies again. And we're going to move up to more expensive ones too. This is what's implemented in a lot of multi-core processors today because it's so simple, right? It's not as bad as a bus, right? This is a ring. You've probably seen rings before. It's different from the rings you have in your hand. But it's kind of, you can stretch your imagination for it to look like it. This is essentially, the processors are connected via local links, and a ring connects all of them, basically. Each processor is connected to the next processor, or each cache is connected only to the next cache and the previous cache. And they can still reach every other cache. Right? And this could be bidirectional or unidirectional. The advantage is cheap. Right? The cost is O(n). Why is it O(n)? Because you really have n links. Right? These are local links. The disadvantage is high latency. Right? It's O(n). Whereas previously it was O log n with the multi-stage networks. And it was O1 with the bus, right? The latency it's a single bus. And this is in terms of the number of hops. So you got to be careful. Because latency is really nanoseconds or some time, right? The bus may have O1 latency in terms of number of hops because you need to go through one hop, but your latency may be very bad as you scale it, as you have a 10,000 core system. This is not easy to scale. I did not talk about bisection bandwidth, but well, there's a reason why I did not talk about it. These networks, I don't want to introduce a lot of terminology on you. These networks, you may hear this, that's why I'll throw out the term for you. The networks are evaluated based on bisection bandwidth. And the idea is, if you take a cut through the network where you have many connections, figure out where the network has the maximum number of connections and look at the bandwidth. Look at how many items you can send per second, if you will, through all of those connections through that cut. That's the definition of a bisection bandwidth. In this case, the bisection bandwidth is very low, right? If you take a cut, what is the bisection bandwidth? I guess it's the link width times frequency times 2, right? In this case. That's the problem. And as you add more links, as you add more processors, this bisection bandwidth remains constant, right? Because you're not really adding more connections. The connections are really local, right? It's part of the ring. But this is a metric that you may hear in terms of the evaluation of networks. That's the idea of the bisection bandwidth. Take the cut that has the highest bandwidth, highest number of links across the network, and figure out its bandwidth, and that's the bisection bandwidth, because you're dividing the network into two sections, and that's the bandwidth. Of course, this is bad because you may not have a lot of bandwidth on this side and on the other side, right? And also, it doesn't take into account issues like contention. That's why I didn't want to introduce you this. Okay. And that essentially leads to high latency, right? In this case. In this particular case, it works because as you add more nodes, you're adding more latency because you're not adding more communication links, if you will. It's only local links. Okay. Nevertheless, it's used in processors today. So IBM Cell, for example, Intel Larrabee, and I think Intel Nehalem also has it, right? Sandy Bridge. Sandy Bridge does. Nehalem doesn't? What do they have? It's a crossbar. Okay. Because Sandy Bridge is cheaper. Okay. Yeah, it's simpler, less costly, and as long as you can tolerate that latency, you can have. It's a good choice. So if you look at a unidirectional link, this is simple, right? If you look at the router that you need for this is the node. Node needs to be able to inject into the ring, and node needs to be able to eject from the ring, if you will. That's why you have this crossbar that's needed, or 2x2 router. So this is just to give you a lower level look into what you need to have. And you could also, of course, optimize the design of this to be simple. Okay. Okay, we already talked about this. Average hops is this, and latency really depends on the utilization. So why could this be good? Just to give you an idea, when you design a program, you may, and if you know that your interconnection network is a ring, you may want to put communicating threads close to each other, right? That way you can take advantage of your topology. Right? For example, if you have two threads that communicate a lot with each other, this is actually nice with pipeline parallelism that I talked about somewhere here. If you have this pipeline parallelism, you can have thread 1 here, thread 2 here, thread 3 here, thread 4 here, and set up a pipeline along the ring. Right? And as long as you put your communicating threads close by each other, you can actually keep the latencies in check, and you can utilize the bandwidth fully. So that's where designing a parallel program becomes interesting. You need to take into account these interconnect design considerations if you want to optimize your parallel program. Right? And that makes it difficult also. It's interesting, but difficult. Okay, let's take a look at some other topologies. Mesh is also another topology that's implemented today in some processors. Well, this is the idea of a mesh. Do I have a better picture of it? Well, unfortunately, I don't. Basically, it's a two-dimensional design, and each processor is connected to its neighboring nodes with a router. And if you want to communicate between this processor to this processor, you go through a bunch of links, and there are routers in between that route your message. Simple, right? Actually, conceptually simple, and you can see that this is easy to lay out also, right? It's nice. You design one tile and stamp it, and verify only one tile. Cost is ON. It's not that costly, right? Average latency is square root of n, and you can figure that out. Easy to lay out on chip, and there's path diversity. So compared to a ring, if you will, a bus has no path diversity, right? There's only one path for everything, if you will. A ring has a little bit more path diversity, and if you can exploit it, you can put things together such that communication happens in parallel. But there's only one way from getting from this node to this node, unless you have a bidirectional ring. Then there are two ways, right? With a mesh, there are many, many ways, right? I don't know, you can figure out how many ways going from one node to another. Of course, now you can design the routers to optimize, to minimize the latency, right? And this is used in the Tyler 100-core processor and many on-chip network prototypes from Intel, especially. Okay, so one problem with mesh is if you want to communicate between this core and this core, if you will, you need to go through all of these routers, right? It's not symmetric, right? It's not symmetric on the edges, at least. Which means that if you place something here, then you need to traverse all the way here to get here. And you also need to traverse all the way here, all the way, these 7 routers in this case, to get to here. But if you added this link, this other link here, that communication would have been much faster. Right? And that's the idea of a torus. That's basically that other link that I showed you here. Now you have even higher path diversity and more bisection bandwidth. So what's the bisection bandwidth of a mesh? Well, you take the most number of links and cut the network through there. In this case, anywhere will do. You have 1, 2, 3, 4, 5, 6, 7, 8 links, and the bandwidth of those links. That's the bisection bandwidth. Well, with torus, you have, how many more do we have we added? I guess we've added 1, 2, 3, 4 more, right? In this case, well, 8 more in that case. Yeah. So your bisection bandwidth doubled, right? And you've avoided that placement problem, if you will. Okay, the downside is higher cost again. It's harder to lay out on chip because now you have unequal link lengths, right? Is that true? Yeah? It is kind of true, although you could play tricks like this. This is a torus too, in one dimension. You could actually, I'll let you think about this, but you could actually lay out, kind of equalize the links by weaving the nodes to make internode latencies almost constant. So it's not impossible, if you will. There are ways of looking at the network such that links are more or less equal. I'll let you convince yourself that this will be a torus as you add more of these things. Okay, there are other networks which we will not go into more detail about that much, but trees are some other networks. Well, we all know about trees, right? And this is a hardware tree, if you will. These are the connections that you have. And this is a way of laying out on chip. So if you look at the tree, maybe it looks like it's terrible to lay out, right? But you could actually lay it out this way, and it could be irregular, right? Latency of the tree is O log n. It's good for local traffic, if you will. For example, if you have something like this, well, if you have 2 nodes communicating here, it's nice, right? Because you have these connections that are close by. Cost is cheap, O(n) again, easy to lay out. The problem is the route can become a bottleneck, right? If you have a lot of communication that's happening between these 2 different sides of the tree, well, there's another route. You could do that over here. Then that route will become the bottleneck, right? And people have developed fat trees to avoid this problem. So you have a much bigger, as you go up the tree, your links become wider. Right? And Connection Machine 5 had this fat tree, if you will. And this is one example of their fat tree. And they actually had multiple different routes also. You could have multiple different routes. I'm not going to go into more detail. If you're interested in this, you can certainly read this paper. It's an interesting machine, connection machine design. It's a very parallel SIMD processor, if you will, single instruction, multiple data. And this is how the processors were connected. Okay, some other networks that you may see. Hypercube, have you heard of hypercubes? Yes? So you could actually connect processors that way. And your latencies are lower, if you will. So, well, I guess with trees also, your latency is log n, right? It's not as low as the Crossbar, of course, but it's much cheaper than the Crossbar, hopefully. Because Crossbar was all n square, right? Whereas here, it's all n log n. And that's a hypercube in different dimensions. And you get low latency compared to a bus or a ring. But it's hard to lay out, it turns out. And this was implemented in the cosmic cube system. And if you're interested in this, you can read this paper. It's a little bit harder to read than the other paper. It was a 64-node message passing machine, and this is the hypercube for the 64 nodes. I think it's 64, right? 2 to the n. Binary 6 cube, that's right. Yes, 64 nodes. And you can see how that is connected. Okay? So a lot of the large-scale supercomputers, this was a supercomputer, actually. This is not a multi-core processor by any means. These are nodes, processors, and you have a big machine room that connects all of these, and these are real wires. A lot of the large-scale supercomputers, like top 500 supercomputers, if you look at them, they have some sort of interconnection networks to connect them. So what do you use them for? For example, you can use them for earthquake simulation or weather simulation, right? You have a problem, simulate the weather, you parallelize it on 10,000 nodes, and nodes need to communicate with each other somehow because you have a single problem that you're solving, right? And that's what this interconnection network is for. You could have coherence, or you could program it with message passing that we briefly touched upon. You still need to communicate. So if you look at the data centers, if you will, that are housing these supercomputers, you have all these big wires that connect these computers, real links. And it turns out the human effort spent to do that wiring is almost as costly as building the machines. Because you need to do that wiring, and you need to do that wiring correctly. Well, how do you do that? Well, some human needs to go through that and do that wiring, right? What if the human connects links to places that are not to a wrong port on a machine? And this has happened before. Okay? What if there's a machine goes down and you need to take it off? Now you need to rewire the nodes, right? How do you do that? So it turns out it's expensive in not only hardware cost, but also human effort to maintain these machines. So that's one of the reasons alternate technologies are interesting. For example, can you actually have these links through wireless communication or through optical communication across different nodes instead of having real hard wires or metals? Okay. I guess, are we done? Well, I have a couple more minutes, so I'll give this to you also. We're done with topology mostly, but you can see there are a variety of design choices. So it's a big design space. The key is you have a big trade-off between cost, latency, and contention, right? And hopefully you'll know the basics of those trade-offs. You'll know the basics, fundamentals of those trade-offs. If you want to design a purely general purpose system, you have to design for the average case. But if you know the specifics of your network, then you can design your parallel program to take advantage of it, right? In a fat tree-based network or tree-based network, you want to exploit locality, right? So for threads that are communication locality between threads. For threads that are communicating a lot, place them to close by nodes, such that they see lower latency of communication, if it's possible. And if you know that those communication patterns. And that makes programming parallel computers hard also. So one thing that I will leave you with is how to handle contention. In all of these networks, you have a switch, right? This is one switch with, I guess, 4 output ports, and let's assume those are also input ports. 2 packets want to go the same direction. That's the definition of contention, right? 2 packets want to use the same resource. How do you handle that contention? Duplicate the resource. Well, without changing the resource. You have only a single resource. Yes, that's one way of doing it, but now you have a different topology, right? If you duplicate the resource, because you're adding more links. But that's a good point, yes. Buffer, yes. So one possible way of handling contention is when 2 packets want to go the same direction, you say to one packet, stop. I'm going to allow this packet. Stop means, well, you have a buffer here that buffers that packet, right? That's one way of handling contention. What else?
Drop one of them.
Exactly, drop one of them. You can drop one of them and tell the sender, I've dropped your packet. Sorry, send it back again later, right?
Or just wait for it to figure it out.
Or what? Oh, yeah, exactly. You could do that also. That's right. Timeouts. And that's used in internet protocols, right? What else? Or should we make it an exam question without revealing what's the other way? Actually, there are other ways. There are 4 ways, I think. Right now, I think of it. I think I've listed 3 here. Buffer drop. So drop is a NAC, right? When you drop a packet, you essentially NAC the source, saying that, sorry, I've dropped your packet. There are 2 other ways. Well, I guess, yes.
Send it somewhere else.
Send it somewhere else. That's right. And that's the idea of deflecting, if you will, or misrouting a packet. Well, you have another link here, right? What if it's free? I don't have to send this packet this direction. Why don't I send it down here, even though it doesn't want to go that way, right? And hopefully, at some point, it'll circle back, as long as the routers know the destination of the packet, and they do. It'll circle back to its destination, right? That's the idea of deflection. That's the 3rd fundamental way. You buffer, drop, or deflect, misroute. Yes?
You could also run these nodes faster than your other nodes. So like if you run it k times faster, if
I guess that's right. You could do that. Then you do avoid contention, right? Okay. Assume that everything is the same frequency. There's another way that's also cheating, I think. The other way that I was thinking of, because in that case contention doesn't happen. You could ensure that contention doesn't happen, right? You could do routing. Before you send the message, you could set up your route and ensure that contention will not happen. That's another way. But basically, if you don't do those, there are three fundamental ways of handling contention: buffering, dropping, and misrouting. And they're all used in different ways in existing networks. Well, we'll assume buffering. That's for the next time, though. Okay, any questions? Next time we may go into interconnection networks a little bit more, or that's the last lecture, so